Okay, this next section is applications of maximum and minimum. So all the things you learned about increasing, decreasing, critical points, inflection points are now going to be put to real world use. So this section is all about word problems and how to solve them. So what I have some strategies for solving max and word problems. Please press pause and copy down the following notes and you're ready to go. Please push play again to watch the rest of the video. Please press pause. Okay. Go over some examples. Okay, for example, find two numbers whose sum is 42 and whose product is as large as possible. So, for example, just to show you some examples here, I think of two numbers who add up to 42. For example, 2 plus 40, and the sum is 42, the product of the two is 80. I also could do 1 plus 41. That sum is 42, but that product is 41. I could add two numbers, say for example, let's see, 30 plus 12. That gives me 42. And when I do 30 times 12, I get 360. So you see, even though all the sums add up to 42, all the products are different. So can you give me two numbers whose sum is 42 and its product is as large as possible? You want a maximum product. So when you start these problems, you always want to have the goal in mind. So the goal, and you want to write this out, is to find a product as large as possible. So in terms of what we just did in calculus, our goal here is to maximize the product. That is our goal. So I'm going to start off, I have two numbers. First number I'm just going to designate as x. I don't know what it is. It could be anything. Now, my second number, I'm going to write it as 42 minus x. Because whatever x is, the second number is going to be that much less than 42. For example, if this number was 10, 42 minus 10 gives me the second number is 32. So whatever you choose for first number, 42 minus it will give you the second number. So that's why my mathematical notation is what it is. So my goal here is to maximize the product, so I'm going to create a product function. So the product of the two numbers, x times 42 minus x, sorry, is p, 42x minus x squared. Again, this is both the first and second number multiplied together. Now, as I'm trying to maximize it, I want to find the max of the product function. I'm going to take its derivative. I'm going to find critical points because remember, if there are a maximum and a minimum, they're going to occur at the critical points. In this case, all I have is 42x. 42 minus 2x equals 0, and I get x equals 21. Now, I only have one critical point, so I got to find out, is it a max or a min? So what I'm going to do, determine if it's a max or a min, I'm going to use the second derivative test. Okay, you could use the sign chart if you like, or you could use second derivative test. I'm going to use the second one. So p double prime ends up being -2, which means my function is concave down, which means my one and only critical point, because critical points are max or mins, the only critical point I have is only going to be a max. So again, this proves that our critical point is a max. Now I substitute this in for x. My two numbers are 21 and 21. They add up to 42, and they give me a product of 441. Okay, another example. Find two numbers whose sum is 50 and whose product is as large as possible. So again, my goal here, I'm going to write this out, is to maximize the product, just so you know what you're looking for. So now my first two numbers, first number I'm going to designate as x, be anything at once. And now since the sum of these two numbers is 50, the second number is going to be 50 minus whatever that number is. Now since I'm maximizing product, I need to have a product function. So I'm going to multiply the two numbers together. So product is 50x minus x squared. Take its derivative to find the critical points. And you get x equals 25. Again, you have one and only critical point, so there is a max or min that's going to occur there. So I'm going to take p double prime. I'm going to use this in the second derivative test. And the second derivative is going to end up being -2. So again, concave down, that means our one and only critical point is going to end up being a max. So I set 25 for x. I get 25 and 25, which gives a maximum product of 625. So again, if I pick any two integers and add them together to get 50, the biggest product you could ever get is 625. Alright, please press pause now and try the next practice example on your own, then push play to go over it. Okay, here's the answer to the practice problem. Okay, next example proof of what you're noticing about the two numbers being half what the sum is. We'll prove that when I get back. On the next slide, a two-dimensional example. So that 40 feet, linear feet, means no line, 40 feet of fencing with which to close a rectangular space for a garden. So I'll draw a picture. There's my garden. Find the largest area that can be enclosed with this much fencing. Okay, so my goal here is to maximize area. So with that in mind, that means I'm going to need an area function. So what I know is I have two sets of dimensions. I have length and width, x and y. Okay, so whichever one, whichever is length, whichever is width. But anyway, all I know is I have 40 feet of fencing. So that means the perimeter, which is going to be add up all four sides, x plus y plus x plus y, is going to add up to 40. And I get 2x plus 2y equals 40 for my perimeter. Now, I know that fact, but my goal here is to maximize area. The area of this thing is going to be x times y. Now I have three variables. I can either do implicit differentiation, which I don't feel like doing, or what I could do here is use this information to substitute variables into the area formula. So for example, I solve one of these for y. So I have 2y equals 40 minus 2x. Y equals 20 minus x. I'm going to take this and substitute in for y. So that now instead of area being x times y, area is going to be x times 20 minus x, which gives me an area of 20x minus x squared. So now which function take the derivative of? Perimeter or area? That's where we write out our goal. Our goal is to maximize area, so I'm going to take the derivative of the area function, because whatever this function is, I want to find its max or min, so I need to find its critical point. That's where the maximums occur. And you get x equals 10. Now to determine if it's a max or a min, I'm going to take the second derivative. A double prime is negative 2. Concave down. So x equals 10 gives us a maximum for the area. So x is 10, and when you can go back, substitute it in for y. You get y is 10 as well. And again, the way I got that is back to the perimeter, and you get y equals 10. Now, since our shape is 10 by 10, which geometric figure maximizes area for a given perimeter, all four sides being the same? You have a square. Okay, please press pause, try the next problem, and then push play again to go over the problem, check your answers. Just use the first one to mirror the second one. Okay, take a look at the second one. Okay, again, same kind of problem. Our goal is to largest area, and I'm given the perimeter is 120 feet. So I brought my units up top. Top is feet as well. So I'm going to draw my picture. Here's my garden. So perimeter is also 2x plus 2y. So I have 2x plus 2y equals 120. Now, since my goal is to maximize area, I need an area function. Area is x times y. Now again, I have three variables, but I want to have two. So what I'm going to do is I'm going to solve this perimeter function for a variable. And it doesn't matter what you solve for. I'll solve for y again. Once I solve for y, substitute it in for y. So my area is x times, instead of y, 60 minus x. Now between the perimeter and area functions, my goal is to maximize area. If it was minimize perimeter or maximize perimeter, you take the perimeter function. We're talking about area. Derivative of the area. Let's see, area is 60x minus x squared. 60 minus 2x. Find where the maximums occur. So get my critical points. And you get x equals 30. Now to solve for y, or determine if it's a max or min, a double prime, negative 2, concave down, so the one and only extreme value is going to be a max. So now finding what y is. You get y is also going to be 30. So again, we have a square.